As telescopes like the James Webb Space Telescope look out across the Milky Way, you might have heard the growing buzz around newly discovered exoplanets. The headlines are exciting. The promises are bold. Earth 2.0 found. New planet could harbor human life. Scientists discover habitable world. It wasn't that long ago, only 1992, that we found the first planet outside our solar system. But since then, over 5,800 have been confirmed in the relatively small area of space, only a few thousand light-years across, that we reside in. When the Milky Way itself is 105,700 light-years in diameter, this offers us a tantalizing promise of billions, perhaps trillions more planets across the rest of our galaxy. Every star on average likely has at least one planet, and perhaps several. With all these exoplanets out there just waiting to be found, it's only natural we would want to turn our thoughts toward Goldilocks zones and planetary habitability. After all, humanity has its eye on colonizing the stars, and an Earth 2.0 is surely waiting for us out there, mathematically speaking. In fact, you might have already heard that phrase, Earth 2.0, being delivered in headlines of articles or videos, claiming that a new planet has been discovered that would be ideal for human life and colonization. However, don't believe the hype. All the planets we've found so far have, to put it scientifically, sucked. And once you hear what I'm about to tell you, you'll agree that moving to any of them will be the last thing any sane person would want to do. I'm Alex McColgan, and you're watching Astrum. Join with me today as I give you the grand real estate tour of the potential Earth 2.0s we've discovered so far, and explain why right now is the wrong time to get onto the planetary property ladder. When choosing an Earth 2.0, just like with buying a house, it's a good idea to start by establishing your non-negotiables. What are the absolute must-haves for human survival? Some of this is fairly simple to consider. For instance, temperature. You want a nice, temperate climate, somewhere that's not too hot and not too cold. Given that temperature drops the further you are from a star, every planetary system has a sweet spot where the temperature of a planet is likely just right, not too hot and not too cold, similar to Goldilocks and her bowls of stolen porridge. As a rough rule of thumb, if a planet is at the right distance from a star, it may well have a suitable temperature for us to set up shop. Of course, this is in no way a guarantee. After all, Venus, a planet residing in this zone, in theory should be perfect. But its choking atmosphere makes it the hottest planet in our solar system, despite its distance from the Sun compared with Mercury. Surface temperatures reach 475 degrees Celsius, hot enough to melt lead. The atmospheric pressure at the surface is 92 times that of Earth, equivalent to being 900 meters underwater. So it's clear that atmosphere also plays a critical part in all this. Speaking of atmosphere, that's also something you'll want to look for on Earth 2.0, ideally something with oxygen and water vapor, and without anything that would poison us. But at the very least, something that could trap heat in and offer some protection from deadly space radiation. However, sometimes a non-negotiable is simply the neighbors that live close by. And this is where our cosmic real estate tour starts to reveal some serious problems. Let's consider the first major reason why the galaxy's exoplanets fall short. Their neighboring stars. Our own star, the Sun, is known as a G-type yellow dwarf, a relatively fast-burning, short-lived sort of star, at least compared to some of the other options out there. Stars like our Sun tend to live for about 10 billion years before their cores collapse, and they transform into red giants. The Sun is stable, and that stability has been absolutely crucial for the life that eventually flourished here on Earth. 4 billion years of consistent, reliable energy allowed life to emerge, evolve, and develop into the complex biosphere we see today. However, yellow dwarfs are far from common in the Milky Way. They represent only about 10% of the total stars. Far more common are the longer-lived red dwarfs, which make up a staggering 75% of the stars in our galaxy. These small, cool stars can live for around 14 trillion years, longer than the current age of the universe. That sounds promising for long-term habitability, doesn't it? Unfortunately for the planets orbiting them, red dwarfs come with numerous catastrophic drawbacks. For starters, red dwarfs have a much closer Goldilocks zone compared to their yellow cousins. They burn less brightly, with luminosities between 10% and a measly 0.125%, that of our Sun's output. So, unless you want to live on a world shrouded in perpetual night, which sounds cold, dark, and depressing to me, and will make growing plants essentially impossible, you'd want an Earth 2.0 to be a lot nearer to its red dwarf star to compensate for that dimness. This proximity wouldn't be a problem in and of itself if it weren't for the second characteristic of red dwarfs that makes them very unpleasant neighbors: their violent instability. Our Sun is the main source of our space weather. It shoots out a frequent stream of solar winds, flares, and coronal mass ejections. We've learned to live with these relatively mild outbursts. Our magnetic field protects us. Our atmosphere shields us. However, this doesn't even begin to compare to the amount of space weather created by red dwarfs. Flares from red dwarfs can be 100 to 1,000 times more powerful than those emitted by our Sun. We're talking about absolutely devastating bursts of radiation and charged particles. The frequent explosions of plasma and high-energy radiation coming from red dwarfs are powerful and dangerous enough to strip away planetary atmospheres entirely and even boil liquid water on planets in the so-called habitable zone. And given how much closer planets must be to their star in a red dwarf system to maintain habitable temperatures, the odds of life getting enough time to arise before being hit with a life-sterilizing dose of X-rays is pretty slim. If you want to live on a planet around a red dwarf, you'll likely need some serious sun protection. And by that, I mean kilometers of solid rock between you and the sky. This rules out many celebrated exoplanets, such as the astronomer favorite Proxima Centauri b, the closest exoplanet to Earth at just 4.2 light-years away. Despite being in the habitable zone of Proxima Centauri, a red dwarf, scientists have concluded that this planet has likely been subjected to so many powerful stellar flares that any atmosphere it once had has been stripped away. While it may be theoretically possible to survive for a time in quite uncomfortable conditions in a deep underground bunker on such a planet, the experience would hardly be pleasant. You'd be trapped underground permanently, never able to see the surface, growing food under artificial lights, completely dependent on technology to recycle air and water. That's not colonization. That's imprisonment. But even during the quiet periods between harsh solar weather events, there's another fundamental problem with planets around red dwarfs: their tendency to be tidally locked. Being tidally locked means that the same side of the planet always faces the star as it orbits. There is no rotation between day and night. One side of the planet bakes in perpetual heat, and the other side freezes in permanent shadow. Think about our moon. The same side always faces Earth. We never see the far side from our planet. That's tidal locking. Due to gravitational constraints, planets close to their stars have a strong tendency toward being tidally locked. Just take a look at Mercury in our own solar system, with its days that last 176 Earth days, or 2 Mercurian years. It's not fully locked, but it's getting there. For planets in the close-in habitable zones of red dwarfs, tidal locking is virtually guaranteed. This lack of rotation could render most of the planet completely uninhabitable. You'd either face scorching, desert-creating heat on the day side, temperatures hot enough to vaporize water, or freezing ice sheets, kilometers thick on the night side, where temperatures plunge far below anything we experience in Antarctica. Even if humans tried to live in the narrow band of twilight that would ring a tidally locked planet, that thin zone between eternal day and eternal night, liquid water might prove extremely difficult to find. Here's why. Any moisture in the air that drifted to the night side of the planet would get trapped there, solidified as ice. Over millions of years, this creates a massive cold trap. All the water on the planet gradually migrates to the night side and freezes solid, locked away from the habitable zone. Overall, the planet would become very dry, and even in the twilight zone where temperatures might be tolerable, there would be no rain, no rivers, no lakes, just endless arid badlands. And that's not even mentioning the weak magnetic field that would likely exist on a tidally locked planet. Magnetic fields are generated by a planet's rotation and the movement of molten metal in its core. A planet that doesn't rotate loses this protective shield, leaving it even more vulnerable to stellar radiation. Living on a tidally locked world would mean enduring extreme winds as air constantly flows from the hot side to the cold side, creating perpetual hurricane-force storms in the twilight zone. It would mean living under a dim red sun that never moves in the sky. It would mean a dry, hostile environment stripped of water. This is not Earth 2.0. This is a nightmare. Let's say, for argument's sake, that we find a planet orbiting a nice, stable yellow dwarf like our Sun. The star is well behaved. The planet has a day-night cycle. It's in the Goldilocks zone. Temperatures are perfect. Problem solved, right? Not quite. Enter Kepler 452b, a planet discovered in 2015 that was immediately dubbed Earth's cousin, or even Earth 2.0 in breathless headlines. It orbits a G-type yellow dwarf star, just like our Sun. It's in the habitable zone. Its year is 385 days long, remarkably similar to our own. The star is only slightly older and slightly brighter than the Sun. In many ways, it looked like the perfect candidate. Scientists calculated that it might have liquid water on its surface. It could have a thick atmosphere. It might even have active plate tectonics. But there's one crushing problem. Literally. Kepler 452b is a super-Earth. It has a radius about 60% larger than our planet, which means its surface gravity is estimated to be roughly twice that of Earth. Let me explain what living under twice Earth's gravity would actually mean for your body. Right now, as you sit or stand on Earth, your body is experiencing 1 g of gravitational acceleration. Your muscles, bones, cardiovascular system, everything about your physiology has evolved over millions of years to function optimally under this exact gravitational load. Now imagine doubling that. Imagine strapping a person to your back, someone exactly your weight, and carrying them everywhere you go, forever. Every step, every movement, every breath. Standing up from a chair becomes exhausting. Walking feels like trudging through deep mud. Running becomes nearly impossible. Your joints ache constantly from the increased load. Your spine compresses under the added weight, potentially causing chronic back pain and nerve damage. Your heart has to work twice as hard to pump blood throughout your body, fighting against the increased gravitational pull. Over time, this leads to cardiovascular stress, elevated blood pressure, and increased risk of heart disease. But it gets worse. Human bones aren't infinitely strong. Under twice Earth's gravity, the risk of fractures increases dramatically. A simple fall that might give you a bruise on Earth could result in broken bones on Kepler 452b. Children's growing bones would develop abnormally under the increased stress. Elderly people would find movement nearly impossible. Even pregnancy and childbirth would become significantly more dangerous under higher gravity. The developing fetus would weigh twice as much, putting incredible strain on the mother's body. The risk of complications would skyrocket. This isn't a place to build a new civilization. This is a slow torture chamber where every moment of existence is exhausting, painful, and medically dangerous. You could survive on Kepler 452b for a time, months, maybe years, with proper medical support. But you couldn't thrive. You couldn't build a society. You certainly couldn't call it home. Well, you might think, what about the opposite problem? What about planets with lower gravity than Earth? That would make everything easier, right? Unfortunately, no. Low gravity presents its own catastrophic health problems, problems we've already observed in astronauts who spend extended periods in microgravity aboard the International Space Station. Consider the Moon, with only 16% of Earth's gravity, or Mars, with about 38%. These might seem like pleasant alternatives to the crushing weight of a super-Earth. But here's what happens to the human body in low gravity. Muscle atrophy. Without the constant resistance provided by Earth's gravity, your muscles begin to waste away. Astronauts on the ISS lose about 1 to 2% of their muscle mass per week, even with rigorous daily exercise. On the Moon or Mars, you'd experience similar degradation. Your legs, no longer needing to support your full weight, would become weak and spindly. Your core muscles would deteriorate. Bone density loss. This is even more serious. In low gravity, your bones don't experience the regular mechanical stress they need to maintain density. The body begins reabsorbing bone tissue at an alarming rate. Astronauts lose about 1 to 2% of bone mass per month in space. This leads to osteoporosis-like conditions, making bones brittle and prone to fractures. And unlike muscle, which can be rebuilt, bone loss may be partially irreversible. Cardiovascular deconditioning. Your heart is a muscle that's evolved to pump blood against Earth's gravity. In low gravity, it doesn't have to work as hard, so it actually becomes weaker and smaller. Blood pressure drops. Astronauts experience orthostatic intolerance. When they return to Earth, they often faint upon standing because their cardiovascular systems can't cope with normal gravity anymore. Fluid redistribution. In low gravity, bodily fluids shift toward the head, causing facial swelling, nasal congestion, and increased intracranial pressure. This can lead to vision problems. Some astronauts have experienced permanent changes to their eyesight after long-duration missions. Immune system suppression. Studies have shown that the immune system functions poorly in low gravity. Wounds heal more slowly. Astronauts are more susceptible to infections. Genetic changes. Recent research has even shown that extended time in space can cause changes at the genetic level, with some astronauts experiencing modifications to their DNA that persist even after returning to Earth. The bottom line, humans are exquisitely adapted to 1G. Too much gravity crushes us. Too little gravity allows our bodies to deteriorate. We need exactly what Earth provides. Let's say, through some cosmic miracle, we find a planet with a stable yellow dwarf star, proper rotation for day-night cycles, and exactly 1G of surface gravity. We still have one more critical hurdle: atmosphere. Just being in the Goldilocks zone doesn't guarantee a breathable atmosphere, or any atmosphere at all. Look at Mars. It's technically in our Sun's habitable zone, at least on the inner edge. But its atmosphere is less than 1%, the density of Earth's, composed almost entirely of carbon dioxide and utterly useless for human respiration. Or look at Venus, which we mentioned earlier. Perfect distance from the Sun, but an atmosphere of thick carbon dioxide with sulfuric acid clouds creates a runaway greenhouse effect that makes the surface hotter than Mercury. What we need is an atmosphere with several specific characteristics. Oxygen. Humans need to breathe oxygen, about 21% atmospheric composition, ideally. Too little, and we suffocate. Too much, and fires burn uncontrollably, and oxygen toxicity becomes a serious problem. Nitrogen. We need an inert buffer gas. Earth's atmosphere is 78% nitrogen, which dilutes the oxygen and prevents everything from spontaneously combusting. Proper pressure. Too thin and water boils at body temperature. Too thick, and the pressure crushes us. Earth's sea level pressure of 101 kilopascals is what our physiology requires. Water vapor. For a hydrological cycle, rain, rivers, lakes, oceans. Without this, the planet is a desert. Protective layers. We need an ozone layer to filter out harmful UV radiation. We need the atmosphere to be thick enough to burn up meteors before they reach the surface. We need it to trap enough heat to prevent ice ages, but not so much that we get a Venus-style greenhouse, magnetic field. Technically not part of the atmosphere, but essential for keeping that atmosphere. Earth's magnetic field deflects the solar wind that would otherwise strip our atmosphere away over millions of years. Finding all of these conditions together, on a planet with the right gravity, orbiting the right type of star, at the right distance, with the right rotation, the odds become vanishingly small. Here's the fundamental truth that all of this points to. Humans have spent millions of years adapting to life on our planet. Every system in our bodies, from our cellular metabolism to our skeletal structure, has been shaped by Earth's specific conditions. We evolved in 1 g of gravity. Our ancestors, who could walk upright, carry tools, and run long distances, had a survival advantage, but only under Earth's gravitational conditions. We evolved breathing Earth's atmosphere. Our respiratory system is calibrated for a specific mix of gases at a specific pressure. We evolved under the light of a G-type yellow dwarf star. Our circadian rhythms, our vitamin D production, even the wavelengths of light our eyes can detect, all shaped by our sun. We evolved with Earth's 24-hour day, our sleep cycles, our hormone production, our body temperature regulation, all synchronized to this rhythm. We evolved drinking Earth's water, eating Earth's organic compounds, breathing Earth's air, living in Earth's biosphere. We're not just residents of Earth. We're products of Earth. We are, in the most literal sense, Earth's children. Our biology is so specifically tuned to this one planet that leaving it means fighting against every system in our bodies. This is the ultimate barrier to colonization. Even if we find a planet that looks right on paper, our bodies are finely tuned instruments that only play one song: Earth. We're just not suited to anywhere else. Here's the frustrating paradox. Earth 2.0 almost certainly exists. With billions of stars in the Milky Way, and trillions of planets, and billions of those potentially inhabitable zones, the statistical probability of another Earth-like planet existing somewhere out there approaches certainty. In fact, astronomers estimate there could be as many as 40 billion Earth-sized planets orbiting in the habitable zones of sun-like stars and red dwarfs in the Milky Way alone. 40 billion potential homes. But here's the problem. Finding them is incredibly difficult. Most of these planets are too far away and too small to detect with our current technology. We can only find planets through indirect methods, watching for the tiny dimming of starlight as a planet passes in front of its star, the transit method, or detecting the slight wobble in a star's position caused by an orbiting planet's gravity, the radial velocity method. Both methods are biased toward finding large planets close to their stars, Jupiter-sized gas giants or super-Earths in tight orbits. Finding true Earth analogs, Earth-sized rocky planets orbiting Sun-like stars at Earth-like distances, is at the very edge of our detection capabilities. And even when we do find candidates, we can't see them directly. We can't study their atmospheres in detail. We can't determine their surface conditions with certainty. We're making educated guesses based on limited data. The perfect Earth 2.0 is out there, but we haven't found it yet. And until our technology improves dramatically, we may never find it. So where does this leave us? We've discovered thousands of exoplanets, and each discovery teaches us something new about planetary formation and the diversity of worlds in our galaxy. That knowledge is valuable. The search is worthwhile. But in terms of finding a new home for humanity, a planet we could actually colonize and thrive on, we haven't found anything remotely suitable. The planets orbiting red dwarfs are radiation-scorched and tidally locked. The super-Earths would crush us under their gravity. The low-gravity worlds would waste our bodies away. The planets with the right gravity don't have the right atmospheres. The planets with the right atmospheres orbit the wrong stars, and even if we did find the perfect candidate tomorrow, Earth 2.0 in every measurable way, we'd still face the insurmountable problem of getting there. The closest exoplanet, Proxima Centauri b, is 4.2 light-years away. With our current fastest spacecraft, that's a journey of over 70,000 years. The more promising candidates are hundreds or thousands of light-years distant, journeys that would take millions of years with current technology. Until we can somehow cross the vast gulf of space between stars, through some breakthrough in propulsion technology or suspended animation or generation ships or methods we haven't even conceived of yet, the question of planetary habitability is almost moot. We can dream about Earth 2.0. We can search for it. We can study it when we find it. But we can't live there. Not yet. Maybe not ever. For now, and for the foreseeable future, Earth is our only home. This planet, with its perfectly calibrated gravity, its breathable atmosphere, its protective magnetic field, its stable yellow sun, its liquid water oceans, its rich biosphere, this is the only place in the known universe where humans can survive and thrive. Maybe that should make us appreciate it more. The grand real estate tour of the galaxy's exoplanets has taught us one undeniable truth. There really is no place like home. And right now, there is no better time to take care of the one planet we've got.